When we use electricity, what do we see at home? Coulombs or amps? Well, I think you can answer this because most of you have probably heard of amps of electricity before, never coulombs. Why is that? Why would we count the quantity when something can't run out? There are current sources in your house. Think about a garden hose compared to a fire hose. The only difference is the flow rate. Neither can run out of water. Nobody can say, don't put that big hose on the tap. It'll run out of water quicker. There's no tank. Okay? So the only time total charge is important is if you're on a battery-powered device. And even then, why would they report coulombs to you? You won't understand it. So they tell you as a percent. Only the people that designed the battery and designed the phone ever considered that. And when you get billed for water and electricity, you pay for the total quantity used each month, but it's expressed as a flow rate. Okay? Let's see how we can convert this in money. Suppose you get paid $10 an hour. This is a current or flow rate. But let's give it a name. Let's call it minimum wage and make a symbol for it, W, and nickname it wager units. So you work for 6 hours. This is the time. Using normal math, quantity is rate times time. You calculate $10 an hour times 6 hours gives you $60. No problem. Remember how we created the astronomical unit? We set the Earth's distance to the sun to the number 1 to get rid of all the extra digits. Let's do the same thing with minimum wage. Let's, instead of saying $10 an hour, let's call it 1W, one wager unit. It's hiding $10 an hour. So now, when we calculate your pay, you get this weird looking thing called 6WH, or 6 wager hours. And a person goes, what did you pay me? 6 wager hours. Well, think about it, doofus. You got 6 wager hours. Each wager hour is $10. Oh, I get it. It's $60. It's weird. It's kind of obnoxious, but it is reporting a total quantity. Okay? That's like saying to someone, how much water do you want in this pot? And you say 4 liters. And you go, I don't have a measuring cup. Okay, turn on the tap. I'll turn the tap on for you to this level. Now count to 5 and you got your total. Let's look at it from electric terms. We have this tank again. It's filled with 10,000 cups of electrons. It's draining at 1 cup per second. So the time to drain is 10,000 seconds. We don't want to really hear it in seconds. So let's convert seconds to hours. 1 hour is that many seconds. So I get 2.7 hours. So instead of saying there were 10,000 coulombs drained in 2.7 hours, we can say there was a flow rate of 1 coulomb a second, which is 1 amp for 2.7 hours. So instead of teaching the public what it is, we just say this sucker flowed at a rate of 1 amp for 2.5 hours, 2.7 hours. And you go, well, what's an amp? It's a cup a second. It's $1 a second. It's a liter a second. All right. You've just simply hidden it. So you see this 2.7 amp hours at the bottom. Still got in there. That means 2.7 cups of electrons every second for an hour. And it is a total. It's just phrased kind of weird. And this winds up how we pay for our electricity. Now let's look at it in terms of batteries. The 4 batteries, there's 1 battery here, doesn't fit in. He's kind of square, doesn't have a lot of friends. You see the one that doesn't fit? That's a 9-volt battery. It's built very differently from these 4. These 4 are identical. So if you bought them all, they have the Energizer bunny on it, and they're all the same. You can easily see that the only difference in these 1.5 volt batteries is they're bigger and bigger tanks. So the total amount of electrons in them is growing proportionally. You can pretty much throw these on a scale and weigh the difference. Or you could measure their volume. It's darn close to that, providing they're from the same manufacturer and they're all, say, alkaline. You can't take one of these to be an old 9 volt or 1.5 volt carbon battery and this one to be a new lithium ion D cell. No. But if you bought them from the same store shelf and they're the same make, you can pretty much weigh them and get the difference. So let's look at how much current they can produce. Now we got this unfortunate little thing called a milliamp. What's a milliamp? It's the same as a millimeter. 12,000 millimeters is 12 meters. So come on, do the math in your head. Move the decimal over 3 places. This is 12 amps, 8 amps, 2.7 amps, 1.2. Each of these batteries, the AAA to the D, can produce this much flow for 1 hour before you kill it. Now, in reality, if you try to do that in an hour, the batteries will explode or get so brutally hot you don't want to do that. But they could do it. So this means the D cell can produce a current 10 times what the AAA battery does. So the D cell is capable of vomiting over all this current flow for an hour, where the AAA can only do this little bit here. But in reality, in many cases, the D cell is just used to last 10 times longer. So how is this actually reporting a total? Because what this is saying is 12 cups a second for an hour. So you'd say, like, how much energy or how much water is in that tank? And you go, this waterfall for 1 hour. So you've reported it something really weird. You said, see that waterfall? Stay here for an hour. That's how much water we need. Or you go, look at this garden hose one over here. How much water is in your swimming pool? This thing for half an hour. Or this thing for 5 seconds. You're reporting a total by taking a flow rate over time. It sounds really weird, but you'll get comfy with it as the years go by. So now this is how we run our totals. Notice this battery says 1000 milliamp hours. What is it saying? This battery can produce 1 amp for 1 hour. How many coulombs is that? 1 coulomb a second times all the seconds in an hour. And then you will get a very large coulomb number. So if you want to know the total electric consumption here, it's the 200 amps times the 2 hours. But the units are weird. The trick is turn this to cups per second and turn that to seconds, and the total will be very easy to calculate. And then if you can't do it, you come and see me, and I will do solutions with this in class.